Hi, welcome to Sunil Maths tutorial, functional analysis class number 62. In this video, we learn this theorem. If P is the projection on the closed linear subspace M of H, then X belongs to M implies Px is equals to X, implies and implied by norm Px is equals to norm X. Let us prove this statement. Let capital H be a Hilbert space and P is a projection. P is a projection on capital H with range capital M. With range capital M. First we shall prove that. First we shall prove that. X belongs to capital M. X belongs to capital M implies and implied by Px is equals to X. X belongs to capital M implies and implied by Px is equals to X. Suppose Px is equals to X. It means then X is in the range. Then X is in the range of the projection P. Of the projection P. X is in the range of the projection P means this X belongs to capital M. Now we prove the converse part. Converse of this statement. We show that Px is equals to X implies X belongs to capital M. So right, suppose that X belongs to capital M. Suppose that X belongs to capital M, I mean range of the projection. We have to prove that Px is equals to X. To prove this, let us take Px is equals to Y for some Y. Now, Px is equals to Y implies as operate on both the sides with P. P of Px is equals to Py, which gives a result of P square X is equals to Py. Already we learned that P is a projection, so P square is equals to P. This gives a result of Px is equals to Py. Again, which implies as Px minus Py is equals to 0, which implies a result of P into x minus y is equals to 0. P into x minus y is equals to 0 means the element x minus y lies in the null space of capital P. X minus y lies in the null space of capital P means x minus y belongs to M orthogonal. M orthogonal is the null space of P. So x minus y belongs to M orthogonal means this x minus y is equals to z for some z belongs to M orthogonal. This condition implies as x is equals to y plus z. Now, in the first stage, we assume that Px is equals to y. So, y is equals to Px. This condition gives us y is equals to Px gives us y lies in the range of P. This condition gives us y lies in the range of P. Y lies in the range of P means that y belongs to capital M. Y belongs to capital M, but we expressed that x is equals to, since here x is equals to y plus z. In this expression y belongs to capital M and z belongs to M orthogonal, and z belongs to M orthogonal. Yes, am I right? So but x is in M, x is in capital M, so we can write x equal to x plus 0 only, where x belongs to capital M, 0 belongs to M orthogonal, 0 belongs to M orthogonal. But what we learned in the previous videos, h is equals to direct sum of M and M orthogonal, h is equals to M direct sum M orthogonal. Therefore we must have y is equals to x, and z is equals to 0. Y is equals to x and z is equals to 0. Therefore, what we choose in the preliminary stage, px is equals to y, and we prove that y is equals to x. Therefore, px is equals to x. Hence, we take the element x belongs to capital M. We prove that px is equals to x. Up to this, we conclude that x belongs to capital M implies and implied by px is equals to x. Px is equals to x. Next, we are going to prove that. Px is equals to x. Px is equals to x implies and implied by px is equals to x implies and implied by norm px is equals to norm x. Norm px is equals to norm x. So let us calculate if px is equals to x. If px is equals to x, this is very obvious. If px is equals to x, then obviously norm px is equals to norm x. Then there is nothing to prove. Again, we take the converse part. Suppose norm px is equals to norm x. Suppose norm px is equals to norm x. Norm px is equals to norm x. This can be written as norm x is equals to norm px. I rearrange the element norm px. I rearrange norm px plus ix minus px. You see here, ix is equals to x. Px also equivalent to x. Already we proved that. So, x minus x you get cancelled. So, this can be written as norm px plus I minus p into x. Now, squaring on both sides. Norm x whole square is equals to norm px plus I minus p into x whole square. So now leave here and we are going to conclude one thing. Now px is in capital M and p is projection. Projection on capital M. This shows us by previous theorem I minus p is projection on M orthogonal. I minus p is projection on M orthogonal means implies as I plus p into x is in M orthogonal. Obviously, it lies in M orthogonal. Therefore, we conclude that px and I minus p, px and I minus px, px and I minus px are orthogonal vectors, px and I minus px are orthogonal vectors. Then by Pythagorean theorem, norm px plus I minus px whole square is equals to norm px square plus norm I minus px whole square because of Pythagoras theorem. So here let it be equation number 2. Here it is equation number 1. From equation 1 and 2 we conclude that norm x square is equals to norm px whole square plus norm I minus px whole square. So you simply from this calculation you get again norm x square is equals to norm x square because norm px is equals to norm x plus norm I minus px whole square. These two terms get cancelled on both sides. You simply get norm I minus p into x whole square is equals to 0. So I minus p into x is equals to 0. This condition shows as I minus p into x is equals to 0 shows as ix minus ix minus px is equals to 0, which implies x minus px is equals to 0, which implies x is equals to px. That is the required condition. Px is equals to x. Hence what we show that here px is equals to x implies and implied by norm px is equals to norm x. This completes the proof of our theorem. Observe that one of the important property or one of the projection of a Hilbert space. All these theorems are defined over the projections. Okay, keep learning. Wish you all the best.